Why does the universe, which is 13.8 billion years old, sound as quiet as death? Think about it. In 13.8 billion years, countless civilizations should have emerged in the vastness of stars. Their traces should be as visible as stars. Yet, all we face is endless silence. Scientists refer to this phenomenon as the Great Filter, meaning that on the way to the stars, there are a series of invisible barriers that keep the vast majority of life from progressing. Next, we need to identify what these most likely barriers are and see how they gradually cut off the path of civilization. Because only by understanding these can humanity answer that ultimate question: are we just getting started, or are we nearing the end? Before the video begins, we must clarify the question: what exactly are we searching for? Is it enough that there is life, even if it's just bacteria or algae? Or are we really looking for civilizations that we can see and hear? If it's only the latter, then the question becomes sharper. Why can't we see them? Think about it. There are hundreds of billions of stars in the Milky Way, many of which may have planetary systems. Statistically speaking, even if a tiny fraction of those planets birthed intelligent life, there should be neighbors other than humanity by now. So why are we still calling out in loneliness without any echoes? Is it because they exist but choose to remain silent? Because they have come and gone? Or is it more likely that they never reached our current position? This is the sharpness of the Fermi paradox. It doesn't ask whether life exists, but whether there are noisy civilizations. So, what does noisy mean? It means loud enough to be impossible to ignore, bright enough to be immediately noticed, and lasting long enough for signals to traverse interstellar space, remaining clear even in our brief window of time. In other words, a noisy civilization should be like neon lights in a city, with signs of energy leakage everywhere, making it impossible to hide. But the fact is, we haven't seen anything at all, which leads us to the key question: why might those potentially existing civilizations not be making noise? Are most of them blocked along the way? What is blocking the way? Is it an unstable environment on a planet? An evolutionary hurdle? Or is it that civilizations stumble in the dangers they create for themselves? If there truly is a series of such thresholds, we need to find them. But the question is, what kind of thresholds count as filters? If the threshold is just a small step that many civilizations can easily jump over, it doesn't qualify as an explanation for why the universe is so quiet. A true filter must be universally present, extremely difficult to overcome, and capable of significantly lowering the survival rate of civilizations. Therefore, before we officially begin our countdown, we need to agree on a method. What standards will we use to determine which thresholds are true filters? We can't just count every little bump along the evolutionary road, right? If it's just a minor obstacle that nearly all civilizations can overcome, then it doesn't explain why the entire galaxy is so quiet. So we need a set of selection criteria. The first criterion is universality. A filter cannot occur only on Earth or only on certain planets. For instance, if there was a special geological disaster at some point in Earth's history, it could only explain whether we were lucky or unlucky, but it can't explain why the entire Milky Way is silent. The question is, which phenomena are universally present, and which are just coincidences on our planet? This is something we need to be especially careful about when judging. The second criterion is difficulty. If a threshold is just somewhat difficult, but ultimately most life finds a way to get over it, then it doesn't count as a filter. A true filter should be one that nearly everyone fails to cross, with only a few managing to succeed. It's like an exam. The real differentiator isn't the easy questions everyone can answer, but the hard ones that almost no one can solve. So what are the hard questions in the long journey of life's evolution? The third criterion is significance. It must have a huge impact on the outcome. In other words, it must drastically lower the final survival rate of civilizations rather than just slowing down the process. For example, some planets might lack a certain element, causing their evolutionary speed to lag behind Earth, but simply falling behind is not impossible. A true filter should be one that completely blocks the path, with almost no room for maneuver. So, the question arises, how many of these absolute barriers exist under the known conditions of the universe? And one must be reminded of a critical weakness in our reasoning. We only have one sample, which is Earth. In statistical terms, this means we can prove almost nothing. but we can only reason from Earth, so we must be especially careful not to mistake the path we've taken as the only path. You might ask, if the data is so limited, how can we compile a list of the top 10 filters? The method is to use the simplest principle, chronological order. We will look step by step at whether there were thresholds blocking the emergence of life in the early universe, whether there were thresholds halting the increase in complexity midway through evolution, and whether there would be thresholds that directly cause civilizations to self-destruct after developing advanced technology. By counting down this way, we can outline the key nodes along the entire path. So next, we will start by looking at the earliest threshold. Consider this. If the parameters of the universe were off from the very beginning, making it impossible to foster life, wouldn't all the subsequent stories become impossible? So let's start with the 10th filter. If the first threshold is hidden within the universe itself, then the question arises, is this machine too picky from the start? You may have heard a saying that the probability of the universe allowing life to exist is 10 to the power of -120. What does this number mean? It's like there's one green spot among countless red areas, and we just happen to be standing next to it. Is this reasonable? Can we really explain everything by luck? Scientists have proposed 3 possible answers. The first is the multiverse theory. Perhaps our universe is just one version among countless others, with the vast majority being lifeless, and only this version allows life to speak, and the reason we can discuss it here is that no one in other universes can even ask the question. But the problem is, if those universes are all silent, what is the point of their existence? Why should we believe it's just probability playing tricks? The second explanation posits that there are deeper rules at play. Perhaps physical constants are not randomly generated, but are constrained by a more fundamental set of laws that force everything into a range suitable for life. But a new question arises. Where do these rules come from? Are they properties of nature itself? Or are they products of a larger system? If there are indeed deeper laws, then the universe we see may only be a superficial layer. The third answer is even more unsettling. This is a manipulated outcome, where someone or some entity has adjusted the parameters to be just right. So who are they? Are they the beings spoken of in religions, high-dimensional civilizations, or entities we can't even imagine? If someone is setting the stage, what are we, humans? Are we actors or experiments? No matter which explanation you lean toward, there's an undeniable fact. If the universe is truly this capricious, our very existence is a tremendous miracle. Then the question arises, this is just the first hurdle. Even if the parameters at the cosmic level are just right, there still needs to be a planet that meets the conditions. What about Earth? Is it truly just an ordinary planet or an extreme exception? Let's think from another angle. With hundreds of billions of stars in the Milky Way, why do we happen to orbit a long-lived, stable, and relatively quiet star? Our sun is neither too large nor too small, burning steadily for billions of years. More fortunate is that Earth is tucked away on the edge of the galaxy, in a relatively quiet rural area, far from the frequently exploding central regions. Is such a position something most planets can encounter, or is it rare and uncommon? Adding to that are the moon's tectonic movements, magnetic field protection, atmospheric composition, and water cycle. Each condition, when viewed individually, may not seem miraculous, but together they resemble a code that is nearly impossible to piece together. Can you call this a coincidence? Or do most planets forever fail to gather this package? If this is indeed an extreme coincidence, then we may have already survived the first filter. But even if the stage and lighting are all set, the questions are still not over. Just because the stage is set does not mean the actors will definitely appear, right? In other words, even if the conditions on Earth are perfect and the universe is finely tuned, does life really just arise automatically? This is the 9th filter, the origin of life. Scientists call it abiogenesis, where life suddenly emerges from lifeless chemical reactions, forming the first system capable of replication and evolution. But the question is, how easy or nearly impossible is this step? On Earth, life appeared very quickly. Within a few hundred million years after the planet cooled, the earliest traces already emerged. Does this mean that life will definitely spring up if given the chance? Or are we just lucky to have stumbled upon a miracle that is almost impossible to repeat? Imagine a planet with oceans, abundant sunlight, and plenty of molecules and minerals, looking no different from early Earth, yet billions of years later, it remains silent, with not a trace of life. Is such a planet possibly common throughout the universe? If so, then Earth's story is not inevitable, but rather an exception. Scientists have proposed many possible starting points. Some say life may have originated in tidal pools, where the cycles of wet and dry act like natural experiments, pushing simple molecules toward more complex structures. Others suggest that deep-sea hydrothermal vents are key, providing a stable reaction stage with continuously emerging energy for molecules. Some speculate that life may have first hidden beneath layers of ice, gradually accumulating complexity through gentle chemical reactions. But which one is the true answer? Or could it be that all of them are possible, but with success rates so low that they approach zero? More extreme hypotheses propose that life's origin requires some special and transient conditions, like natural reactors that may have existed in early Earth, providing unique energy scenarios that might have triggered a key reaction. But how many planets can sustain such conditions over long periods? Could it be just a fleeting stroke of luck? If such unique triggers are necessary, then the ticket to life would be much more expensive than we think. This also explains a dangerous possibility. There may be countless planets in the universe with conditions almost complete, but stuck in a state just shy of being able to leap forward, where chemical molecules circulate back and forth, always just one step away from escaping. Imagine a cosmic experiment where one test tube fills the lab table, most of them inactive, while only a few spark with life. Was our Earth's occurrence inevitable or purely accidental? If life is indeed easy to emerge, then there should already be countless planets in the Milky Way that have crossed this step. So why have we received no signs? If life is truly difficult to emerge, does that mean we have already passed through the hardest threshold? Among these two possibilities, which one is more unsettling? More importantly, even if the sparks ignite, they can extinguish at any moment. The earliest forms of life may have been so fragile that a single environmental fluctuation could wipe them out. Perhaps Earth has also experienced countless failed attempts, with only one lucky enough to survive. But the question arises, can we take this stroke of luck as an inevitability? If the starting point of life is indeed extremely difficult to cross, then humanity may have already won the most unlikely round in the cosmic competition. But that's not enough, because the emergence of life is one thing. Whether it can continue to evolve beyond the microbial world into more complex layers is another new filter. This is the eighth filter, complex cells. Scientists call it the emergence of eukaryotes, life forms with a nucleus and mitochondria. But the question is this step an evolutionary inevitability or a cosmic-level coincidence? On Earth, the earliest life forms were single-celled prokaryotes, like bacteria and cyanobacteria, which were simple, resilient, and had incredible adaptability, dominating the Earth for over 1 billion years. But here's the issue. If they were so successful, why evolve complex cells? What are the benefits of complex cells? The key lies in energy. Prokaryotes act like tiny batteries with limited power, only able to sustain small-scale life activities, while complex cells gain a tiny power generator through endosymbiosis. One cell engulfs another but does not digest it. Instead, they cooperate, and the engulfed cell becomes an energy factory, providing a continuous supply of energy to the host. But the question is, how likely is this kind of engulfing cooperation to happen in the universe? Some say this could be a 1-inch, 100,000 miracle because, in most cases, engulfing simply means digestion, and long-term coexistence is virtually impossible. If this is the case, then the emergence of complex cells is an exceptionally rare event. In other words, there may be countless planets stuck in the bacterial era, forever unable to welcome plants, animals, and humans. If that is indeed the case, have we already crossed the second huge threshold? But some also feel that this step may not be that difficult. After all, plants also have chloroplasts, which they obtain through a similar process, and perhaps this kind of endosymbiosis is more common than we imagine. So the question arises, which possibility should we believe? Is it almost impossible, or is it actually quite common? Imagine again, if complex cells are indeed extremely rare, what would that picture look like? The universe is filled with planets teeming with bacteria and microorganisms, oceans possibly full of plankton, and the air thick with the scent of cells. Yet there will never be fish swimming, trees growing, or civilizations looking up at the sky. A living universe, yet forever stuck at the microscopic level. Do you think such a universe is thriving or desolate? On Earth, complex cells appeared about 2 billion years ago, marking a turning point. Without that engulfing cooperation, there would be no large organisms, no multicellular life, and certainly no intelligent civilizations. In other words, all of our existence may hinge on that one chance encounter of engulfing and digesting. Think about it. Doesn't that make you a bit uneasy? Scientists have also proposed a hypothesis. Without sufficient energy budgets, the complexity of life could be permanently stifled. The energy limits of prokaryotes restrict their number of genes and cell sizes, making it impossible for them to evolve nervous systems and complex organs. But the question arises, if most of the life in the universe is stuck at this energy bottleneck, are we even more alone? Thus, the eighth filter presents a cruel possibility. The universe may not lack life, but may lack complex life. Perhaps oceans are common, bacteria are widespread, yet planets that manage to take that leap into complex cells are few and far between. If that is the case, then humanity's very existence is already an extreme miracle. But even if we have crossed the threshold of complex cells, the questions are still not over. Complex cells may have more energy, but each single cell remains isolated. So the next question is, do they need to learn teamwork? Thus, the seventh filter emerges, multicellular life. Sticking a few cells together isn't hard, but does that count as multicellular? If each does its own thing, scattering at the first sign of trouble and consuming resources internally, how long can such a team last? True multicellularity requires clear division of labor and mutual dependence. A single cell cannot survive long on its own. Why is this step difficult? The difficulty lies in the costs and risks. First, let's look at costs. For a team to be stable, they must stick together. Cells need a whole set of glue and zippers. Adhesion proteins fix them together, communication pathways allow them to coordinate, determining who should divide, who should stop, who becomes muscle, and who becomes nerve. Without these, the team is either scattered or chaotic. So the question arises, where did these molecular switches come from? Is one or two mutations enough, or do we need a whole package of new parts to come online together? Now, let's consider the risks. Division of labor means sacrificing some freedom. Who prevents cheaters? If a cell doesn't follow orders and just keeps dividing for its own benefit, what happens? Today we call that a tumor. Was such internal strife more common in the early multicellular world? To suppress cheating, there must be oversight. Mechanisms like programmed cell death, suppression pathways, and immune patrols. So the question arises, which comes first, oversight or cooperation? Cooperation without oversight cannot last. Only with oversight can long-term division of labor be discussed. How can this chicken and egg order be crossed? The environment must also be competitive. Large volumes require high energy and high supply. Without sufficient nutrients and resources, huge bodies cannot be sustained. If oceans or atmospheres are constantly flipping, and the team is barely set up before collapsing, who would dare to invest long-term? How many planets get stuck at this step? They may have oceans, chemistry, and blankets of microorganisms, yet can never leap past the threshold of size. Can you imagine a bustling yet microscopic planet? The surface is full of life. Yet looking across, there are no trees, no fish, and no animals that can look up at the sky. Earth's records give us a reference. True multicellularity has appeared more than once, with one branch for animals, one for plants, and one for fungi, while certain algae and bacteria have also undergone varying degrees of collectivization. This sounds like it's saying this hurdle isn't difficult, but we need to be cautious. Earth is the only sample we have, and sticking together doesn't equal proper differentiation. Many so-called multicellular forms resemble temporary cooperatives, loosely aggregated, with divisions that can dissolve at any time. What truly makes complex bodies possible is deep differentiation. Muscles can exert force, nerves can transmit signals, epithelium can seal, and immunity can patrol. Missing any piece makes it unworkable. Is this entire set really easy to replicate? Delving deeper, multicellularity also needs to learn long-term planning. Which grows first? Which tissues get priority for blood supply? And which growth phases to push through? Behind this is a complete developmental program. Developing as a project requires not only writing processes, but also resisting interference, temperature fluctuations, nutrient shortages, and radiation noise can all lead to deviations in the process. Can developmental programs run stably on other planets? Or do they crash halfway through? There's also an often overlooked point. Larger individuals must have their own internal ecology. We host vast communities of microorganisms within us, aiding in digestion, training immunity, and synthesizing molecules. Without this layer of internal ecology, the metabolism and defenses of large multicellular organisms might not hold up. So the question arises, the success of a large organism actually relies on the cooperation of many small partners within. Can this ecological package synchronize its emergence elsewhere? Or is Earth just fortunate? You might ask, since multicellularity has appeared several times on Earth, doesn't this hurdle count as past? Cautiously speaking, primitive multicellularity may not be rare, but a deeply differentiated multicellular system is likely where the filter truly exerts its influence. Because only through deep differentiation can there be organs, organ systems, and ultimately, the nervous system and behavioral complexity. Without it, the world may forever remain at the level of sponges and algae. With it, higher functions like movement, sensation, hunting, defense, and memory become possible. So how did Earth cross this hurdle? On one hand, it might be due to the energy foundation provided by a long-term increase in oxygen. On the other, the gradual stacking of gene regulatory networks to create more stable developmental programs, and also ecological pressures pushing individuals to evolve. In the competition of predation and survival, those who organize better tend to survive longer. But can these three elements synchronize in other worlds? How long would it take to come together? Could it be that most planets falter on one of these aspects, losing all their previous progress? Speaking of which, a new question arises. Even if multicellularity and differentiation are resolved, can the speed of evolution keep up? The larger the team, the heavier the metabolism, and the slower the generational turnover. If genetic changes can't keep pace with trial and error, could complex systems become fixed? Thus, the next key issue surfaces. Is there a mechanism that can maintain stability while rapidly reshuffling when needed? This is precisely what the next threshold aims to answer. The sixth filter, sexual reproduction and genetic innovation. Why don't we suppress cloning? What does mixing and recombining really bring? Without it, how far can complex life go? Imagine if all life relied solely on asexual reproduction. What would that picture look like? The copying speed is incredibly fast, efficiency astounding, requiring almost no resources to find mates. But the problem is, this kind of reproduction resembles a photocopier. A copier can infinitely duplicate a document, but errors will also be copied over. A bad gene could be passed down through generations, increasingly accumulating and ultimately trapping the entire population in a predicament. So the question arises, if asexual reproduction is so fast, why have many forms of life on Earth ended up choosing sexual reproduction? The advantage of sexual reproduction lies in shuffling. Two individuals mix genes, producing entirely new combinations each generation, allowing bad genes to be eliminated, good genes to accumulate, and at critical moments, a trump card can be played. It's like playing cards. You can keep using the same old deck, but the risk is that bad cards accumulate. Sexual reproduction resembles shuffling the deck each time. Although it takes time and effort, it always preserves the opportunity. The question is, can life in the universe evolve this mechanism? Or did we just happen to stumble upon this shuffling miracle? What's more troublesome is that sexual reproduction is not cheap. It requires complex cellular mechanisms, pairing and reproductive behavior, and demands huge energy investments. Many species even need to evolve methods to attract mates and strategies to protect offspring. With so many additional burdens, why does evolution still persist on this path? Could it be that this path only truly brings advantages in extremely rare circumstances? Scientists have found that mechanisms of sexual or quasi-sexual reproduction have actually appeared more than once on Earth. Some single-celled organisms exchange genes under environmental stress, while plants and fungi have their unique sexual processes. It seems this path isn't the only option, but upon closer inspection, does that really indicate it's easy? Or does it suggest that in harsh environments, only through the mixing of genes can life have a chance to continue climbing upward? Imagine again, if there were no sexual reproduction, would complex life inevitably fall into a deadlock? Regardless of how large or complex individuals are, with slow generational turnover, few mutations, and insufficient diversity, can they survive significant environmental changes? If the answer is no, then does it indicate that the life on most planets in the universe, even if they cross the multicellular threshold, might ultimately stall at a relatively complex but lifeless stage? Thus, the sixth filter reminds us that for complex life to continue evolving, it must learn to play high-risk, high-reward games at the genetic level. It's not just a choice of reproductive methods, but a turning point for whether evolution can continue. The question is, how common or rare is this turning point in the universe? But even with genetic shuffling, complex life could still remain at relatively simple forms, just like the early multicellular life on Earth, much of which were merely sponges and algae, quietly staying in place. So how can we usher in a true explosion of life, pushing it toward a rich animal world? This leads us to the fifth filter: complex animal life. On Earth, life struggled for over 3 billion years under the microscope, spending most of that time at the surface of the sea, at levels like algae and plankton, until about 540 million years ago, a sudden change occurred: the Cambrian Explosion. In just tens of millions of years, the diversity of life surged as if on steroids, with various bizarre animals emerging simultaneously, featuring nervous systems, eyes, exoskeletons, and muscle tissues. The question is, why did life suddenly explode at that moment? Scientists have proposed several possibilities. The first is an increase in oxygen concentration. In a higher concentration environment, metabolic efficiency greatly improves, allowing animals to grow stronger and remain active. If oxygen levels had always remained low, would the world have forever stayed in a quiet sponge realm? The second is gene innovation. For example, the emergence of Hox genes allowed body structures to be modularized, assembled like Lego bricks. They determine where eyes grow, how limbs form, and how body symmetry is arranged. Without these genetic tools, complex bodies cannot even be discussed. So the question arises, is the emergence of such genes a universal phenomenon or a random mutation? The third is ecological pressure, a continuous arms race between predators and prey like an ongoing Cold War. You evolve faster swimming abilities, I evolve tougher shells. You grow sharp teeth, I develop more sensitive eyes. Without this relentless competition, would life remain in a state of passivity? The Cambrian seas resembled a life experiment, with massive limbs extending to hunt, trilobites dragging their shadows along the ocean floor, and bizarre creatures extending tentacles to seek prey, various biological forms emerging as if nature suddenly opened the floodgates for creativity. But the question is, could such scenes only unfold on Earth? If we switch to another planet where oxygen doesn't increase, genes don't innovate, and predation pressures are insufficient, would the Cambrian explosion never occur? Imagine another scenario. A planet without complex animals, where oceans are filled with countless cells, microbial blankets cover the shallows, everything is alive yet eerily quiet, with no conflicts, no predation, and no possibility of intelligence. Such a world may seem lively on the surface, but is monotonous in reality. Do you think such a universe is filled with life, or is it still silent? There's a more brutal fact. Even after Earth experienced the Cambrian explosion, it was not smooth sailing. In the subsequent hundreds of millions of years, Earth underwent multiple mass extinction events, with volcanic eruptions, climate changes, and asteroid impacts repeatedly pushing complex animals back to square one. If any of those extinctions had been more thorough, Earth might never have had a chance to rise again. So the question arises, do these resetting events occur more frequently on other planets? If every time life painstakingly climbs a step, it's immediately knocked back down again, wouldn't the chances of civilization be repeatedly diminished? Thus, the fifth filter tells us that the foundation of civilization is not just whether life exists, but whether there is an appropriate explosion. The Cambrian Explosion was like a cosmic lottery, switching the speed of evolution from slow to fast. Without that great explosion, humanity would not exist at all. But even if complex animals take the stage, the road to civilization has only just begun. To nurture intelligence, another key condition is needed, allowing the brain to have the opportunity to grow slowly. The question is, what does the brain's growth require? The answer is, surprisingly, that it requires a long childhood and the ability to collaboratively raise young. This is the fourth filter: prolonged childhood and cooperative child-rearing. Imagine if a species young must be independent just a few months after birth. What would happen? They wouldn't have time to mimic their parents' behavior, let alone accumulate complex experiences. At most, they would learn instinctual hunting and escaping, facing the world alone. A brain like that, even with great potential, has no room to grow. The question is, do most lives in the universe get stuck in this crash course mode? Look at examples on Earth. Antelope and fawns can run just hours after birth, or they'll be caught by lions. Young birds have to learn to forage just days after hatching, or they will starve. This kind of accelerated childhood allows species to reproduce efficiently, but the cost is that there is no time to develop complex social skills. In contrast, human infants require years of care, learning from the group for over a decade, and young ones usually need to stay with their mothers for more than 10 years. Why is there such a huge gap? The key lies in brain development. The more complex the brain, the longer the loading time required. The human brain needs to grow continuously during a long childhood, establishing neural connections and learning language and culture. If this time is shortened, children cannot learn complex skills, let alone accumulate knowledge over generations. In other words, a prolonged childhood acts like a startup time for the brain. Without it, intelligence cannot even begin to run. The question is this luxurious growth pattern common in the universe? Or is it a risky endeavor that only a few species dare to attempt? But just having a childhood isn't enough. The real key is cooperative child-rearing. Parents must provide long-term support, the group must offer protection, and food must be consistently available. Humans even include grandparents, neighbors, and even non-relatives in the nurturing system, where grandmothers help care for grandchildren, elders pass on knowledge, and the whole group has clear divisions of labor, which some call the grandmother hypothesis. It is precisely because elders can transmit knowledge that human wisdom continues to accumulate. Can you imagine how rare this might be in the universe? How many species can transcend individual instincts to establish such cross-generational cooperation? Now, imagine another scenario. On a planet, animals are abundant and the ecosystem is lively. But every young must be independent within a few months. They can hunt and reproduce, but they have no time to establish complex cultures, making the transmission of experience impossible. Such a world may seem vibrant on the surface, yet it will never spark the flame of civilization. So the question arises, is the necessary condition for civilization's emergence precisely this extremely rare communal support? Thus, the fourth filter reveals a cruel possibility. There may be countless intelligent animals in the universe, yet only a tiny fraction can allocate enough room for wisdom to grow. Without a prolonged childhood, intelligence can only remain potential. With it, civilization truly has a chance to be born. But even when the seeds of wisdom emerge, they remain fragile. Imagine if Earth's climate fluctuated violently, resetting civilization before it could even learn to write. Would we even exist today? So the next key question is, can a planet's environment remain stable for the long term? This is the third filter: long-term climate stability. Life is tenacious. It can survive in volcanic craters, deep-sea fissures, and frigid wastelands. But complex civilizations are extremely fragile. If glaciers advance a few hundred kilometers, continental ecosystems can collapse. If temperatures rise a few degrees, it can rewrite the entire ocean's face. A small asteroid impact can plunge Earth into a decade of darkness. So the question is, how many planets in the vast universe can maintain relative stability over billions of years? Earth's fortune lies in its repeated buffeting, yet it has never been completely destroyed. Dinosaurs went extinct, and mammals took over. The Ice Age came, and humanity learned to use fire and caves to fend off the cold. We seem to be advancing through a series of disasters, finding gaps to push through. If any one of those mass extinctions had been more severe, such as a larger asteroid or a longer volcanic chain eruption, would humanity even have appeared? And on other planets, are such fatal deviations more common? Remember, climatic stability is not a gift from the heavens, but a miracle from a series of conditions stacking together. Stars must burn steadily, not fluctuate between hot and cold. Orbits must be stable, not swinging like a seesaw. A planet's interior must have tectonic activity, continuously recycling carbon dioxide to avoid runaway greenhouse effects. There must also be magnetic field protection against stellar winds and cosmic rays. If any one of these links is missing, a planet could quickly head toward desolation. Look at our neighboring Venus, which is similar in size to Earth, yet due to uncontrolled greenhouse effects, it has turned into a hellish 400 degrees. Mars once had water and atmosphere, but due to its small size and weak magnetic field, its atmosphere was blown away, leaving only dry, cold deserts today. They all came close to success, but ultimately lost the stage. The question is Earth the only lucky survivor in the cracks? Imagine another scenario. A planet has just birthed complex life and hasn't had time to develop culture before being wiped out by a global freeze. Or a star suddenly increases in brightness, turning the planet into a desert. This cycle keeps happening, with life forever stuck at the reset stage right after it begins. Such a universe seems to be teeming with life, yet has never truly birthed civilization. Even more cruelly, stability is not a linear guarantee, even for Earth. We have experienced magnetic field reversals, supervolcanic eruptions, ice ages, and may have even faced a snowball effect that nearly brought life to zero. Humans on Earth just happen to appear in a relatively mild gap. If our timeline were pushed forward by a few million years, coinciding with a global freeze, would we not be here discussing the Fermi paradox today? Thus, the third filter poses a sharp question. Can civilization only grow in the cracks? Without stability, the spark of intelligence cannot ignite. If stability is too brief, the spark just ignites and is snuffed out. The question is Earth's stability a universal law of the cosmos or an extreme coincidence? Therefore, long-term climate stability might be the rarest stage for cosmic civilization. Without it, civilization, no matter how intelligent, cannot last long. With it, intelligence has the opportunity to move toward a distant future. But even if the stage is stable, civilization must learn to turn potential into reality. Being smart does not equal knowing how to make fire, and knowing how to make tools does not equate to developing technology. This leads to the second filter, the intelligence that can generate technology. The question is, how many intelligent beings in the universe remain forever as clever animals rather than becoming civilization builders? Let's start with the most straightforward question. Does being smart equal making tools? Clearly not. There are many intelligent beings on Earth. Crows use branches to fish for insects. Dolphins can teach hunting skills. And octopuses even use coconut shells as portable armor. These behaviors indicate they have memory, creativity, and the beginnings of culture. But the question is, can their intelligence accumulate and be passed down through generations? Can it upgrade into increasingly complex technologies? Humanity's uniqueness lies not in being smart, but in stacking that intelligence. It's not about who first ignited the fire, but who could preserve the knowledge of using fire across generations. It's not about who could create tools, but who could continuously improve upon those foundations. The question is this accumulated wisdom rare in the universe? Looking at our own timeline, some of our ancestors used fire over 1 million years ago, yet it wasn't until 20,000 years ago that bronze smelting emerged, and that was just a few thousand years. Intelligence appeared long ago, but the real technological explosion came much later. So if intelligent beings on a certain planet did not experience these accidental breakthroughs, would they forever remain clever hunters instead of civilization creators? Another key point: social structure. Technology is not an individual endeavor. It is a product of the group. One person can create a master, but to build ships, cars, or telescopes, collaboration, division of labor, and cultural transmission are needed. The question is, how many intelligent beings in other corners of the universe can meet all these conditions simultaneously? They must have both flexible hands or similar manipulative organs and a complex language system along with stable community living. If any link is missing, the path to civilization may be severed. Imagine if humans had no language and could only communicate through gestures. How far could our technology go? If we had no hands and could only use our mouths or calls to operate, could we enter the industrial age? If human society collapsed and we faced conflicts within small groups, could we establish cities and science? The answers to these questions point to one conclusion. The threshold for intelligence to transform into technology is extremely high. Ironically, even if technological civilization emerges, it does not guarantee we will reach today. Humanity took hundreds of thousands of years to enter agricultural society and then thousands more to enter the industrial age. If any stage in between was interrupted, such as a larger volcanic eruption or a longer ice age, would we be forever stuck in the hunting and gathering phase? So the question arises, are civilizations on other planets also potentially stalling at such critical points? The cruelty of the second filter is that while there may be many intelligent animals in the universe, very few can convert that intelligence into technology. We might just be that extremely small fraction that happens to have climbed the ladder of technology. But even so, the test is not over. What truly makes civilizations disappear is not necessarily the external environment, but possibly ourselves. Once technology is developed, species face entirely new threats. War, nuclear weapons, artificial intelligence, ecological collapse, these could all become new self-destruct buttons. This is the first filter, late-stage technology and self-survival. Imagine a civilization that has struggled to cross numerous thresholds, from the origins of life and complex cells to multicellular cooperation. Finally able to create technology, but when they finally harness the power of their planet, they suddenly realize they are holding a double-edged sword. Fire can bring warmth, but it can also burn down homes. Nuclear energy can illuminate cities, but it can also destroy entire civilizations. The question arises, can a civilization survive under the weapons it creates? Humanity is a stark example. In the 20th century, we invented nuclear weapons, and the first test made humanity realize we finally had the capability to erase ourselves from the Earth. During the Cold War, how many times were we just a wrong command away from the abrupt end of human civilization? The question is, will other civilizations also encounter similar crossroads? Do all species that enter the industrial age have to face this test? And nuclear weapons may just be the beginning. As technology accelerates, new threats emerge one after another. If artificial intelligence goes out of control, could it eliminate its creators? If genetic engineering is misused, could it create uncontrollable organisms? If excessive resource exploitation leads to ecological collapse, could civilization starve to death in the ruins of technology? These are dangers that late-stage civilizations must face. More cruelly, destruction is often easier than construction. A city may take hundreds of years to build, but can turn to ruins in a single war. A civilization may take thousands of years to reach the edge of interstellar space, but a single global conflict could send it back to the Stone Age. The question is, how many civilizations can survive in such a cycle of repeated games? From another perspective, the late-stage filter may not be a one-time major test, but a series of long-term trials. Can we avoid war? Can we manage artificial intelligence? Can we overcome the energy crisis? Can we maintain social stability? Each question could become a deadly trap. Any failure could leave civilization stalled within the planet, never reaching the stars and the sea. The question is, are we currently walking on this tightrope? Imagine another picture. There may have once been countless civilizations in the Milky Way, all reaching a similar stage as we have, building cities, inventing electricity, entering industrial society, only to be torn apart by wars, self-destructing in uncontrolled technology, or perishing in environmental collapse. Thus, the entire universe appears so silent. The question arises, could we be next? However, there is another possibility. If civilizations can survive and learn to manage their power, then they have the chance to truly venture into outer space. Perhaps some civilizations entrust themselves to machines, allowing future forms to be no longer flesh and blood but steel and silicon. Perhaps some civilizations learn to coexist with the ecosystem, binding development and environment together, never repeating the cycles of destruction from the past. The question is, will such civilizations be common or extremely rare? The first filter is terrifying because it may be unfolding right before our eyes. We are the samples being tested, with the next few hundred years determining whether humanity becomes a resounding alien civilization or just another assistant on countless silent planets in the universe. Thus, the late-stage filter poses an ultimate question. Can we survive the dangers we create? If we can, we may become the loudest voice in the Milky Way. If we cannot, the silence of the universe will have its explanation. Civilizations always destroy themselves, just when they are closest to success. At this point, we have traversed 10 possible filters, from the universe's initial physical constants to the origins of life, from complex cells and multicellular cooperation to the long childhood and technological civilization, and finally, to whether we can survive before self-destruction. It sounds like a checklist, one that can be ticked off one by one, but the real cruelty lies in the fact that these filters do not exist independently. They are layered on top of each other. Imagine if each filter has a pass rate of 50%. The actual probability would be 1/1,000. What if the pass rate of one of those filters is only 1/10? After stacking, the entire universe might be left with only a few civilizations. The question is, did we just happen to step on this extremely low probability path, or do many of the filters not actually have the harshness we imagine? Scientists often use the cumulative trap to explain the silence of the universe. Perhaps the universe is not lacking life, not even lacking complex life, but when you line up all the filters, most planets fall behind at some step. For example, some planets may fail at the step of life origin, some may cross multicellularity but be reset by drastic climate changes, and some may give birth to intelligence only to ultimately die by their own weapons. Each pathway has a different ending, but the final result is strikingly consistent. They all fail to reach the stars and the sea. Ironically, filters are not only natural but also temporal. In the 13.8 billion years of the universe's history, the window suitable for civilization to emerge may be pitifully short. Stars are too young, elements are insufficient. Stars are too old, energy is depleted. Civilization must appear exactly during the golden period. Are we in such a narrow temporal gap? If so, we should be even more vigilant. This window will not remain open forever. Stacking these filters reveals an unsettling picture. Civilization is not rare, but nearly impossible. We may have already passed through most of these checkpoints, yet still stand on the final tightrope. The question arises, are we just beginning, or have we already passed the most dangerous moment? Some say the filters might all be in the past. We have fortunately crossed the origins of life. Complex cells have appeared, and civilization has reached today. If that is the case, then we are the pioneers of the universe, perhaps truly having a chance to be among the first loud interstellar civilizations. But another possibility is more unsettling. Most filters are still in the future, and the late-stage trials have not yet begun, meaning that humanity's future is the real suspense. Thus, the cruelty of the filters lies not in which one is the hardest, but in the way they overlap, nearly erasing all possibilities. Whether we can survive depends on whether we can realize we are on this carefully filtered path. When we reflect on these 10 filters, we find a glaring fact. The silence of the universe is not due to too few problems, but too many thresholds. Each checkpoint acts like a cruel sieve, keeping the hopes of countless planets and countless lives outside the door. To have come this far, we are already among the rare survivors. But the question is, where does this road lead? Some say the silent galaxy indicates we might be the earliest civilization. Perhaps in the entire observable universe, we are the first species to cast radio signals into the sea of stars. If that is true, then the responsibility on our shoulders is heavier than we imagine. We must set a precedent for the entire universe and become the first echo. But do we truly have this capability? Some are concerned that the silent galaxy suggests harsher filters lurk ahead. perhaps nearly all civilizations will end in late-stage self-destruction. Nuclear weapons, artificial intelligence, ecological collapse, these are not science fiction, but realities already before us. The question arises, how far can we go? Will we, like countless invisible civilizations, suddenly disappear before we can break free from our home planet? There is another possibility. The silent galaxy does not mean non-existence, but rather that civilizations choose silence. Perhaps they see the risks and decide to hold back their brilliance, quietly surviving. The question is, should we emulate this caution or bravely spread our voices throughout the universe? Regardless of which answer we choose, the silence of the universe reminds us that humanity is at a crossroads in history. We could be the lonely first voice in the universe, or the next echo to vanish. We might be a beam of hope in the silent galaxy, or perhaps one day be completely erased. Therefore, the real question is not whether there are others in the universe, but whether we can live long enough. If we can pass through the late-stage trials, perhaps millions of years from now, humanity will build cities in the orbits of stars and steer fleets toward the edge of the galaxy. At that time, the silence of the universe will be broken, and the first song will come from us. But if we fail, the universe will remain silent, with just another voiceless Earth added to it. Ultimately, the Fermi paradox leaves humanity not only with questions, but also with warnings. The silent sea of stars acts like a mirror, forcing us to confront ourselves. Are we the first lucky ones in the universe, or the next name destined to disappear? The answer is not written in the starry sky, but in our own hands.